is what is known as a model shell. Okay, what a model shell is, it is a little more abstract than most of our problems because every component of the model is a variable. Okay, so you'll see, it's talking about B dollars and F dollars, and we make D dollars per day and all those good things. So it keeps everything as a variable. And the way I like to attack these, and systematically, is the first time I go through a question like this is I try to write down what I know. In my own words, I try to write down this equals that, this equals that. Then sometimes as an intermediate step, I try to write it down in English. Like, what are we deciding? That's the decision variables. What are we trying to maximize? And what are our constraints? And then I go to the mathematical model. So, it shouldn't come to you like some kind of Rain Man experience where you just go from here to, to the mathematical model. It does take a little bit of time to develop this. So Informs has contracted with Sentinel Security to provide security service for its upcoming 3-day, 4-night national meeting in New York. So one thing we got from there is this conference is 3 days and 4 nights. Okay, that's something that we may need to use. At a cost of B dollars. So B dollars is the fixed cost or fixed contract for this conference. During the meeting hours from 8 a.m. to 6 p.m., okay, so I guess that's the day. The day goes from 8 a.m. to 6 p.m. We pay our guards D dollars. So this is the day rate. Okay, and during the evening, we pay them E dollars per hour. So that is the evening rate. Okay. Informs requires that at least N guards be on duty during the evening. So N is the minimum number of evening guards. And during the day there should be at least 2 guards, as well as 1 additional guard for every 1,000 people. So during the day we need 2 guards plus 1 per 1,000 people, or attendees, if you will. In addition to paying for its guards, Sentinel expects to have fixed expenses of F dollars. So these are our fixed expenses. So that's F. And net profit during the meeting, net profit to the firm is attained by subtracting its payments to its guards plus the fixed expenses from the contracted amount negotiated with Informs. And then part A says, formulate a model shell for this simplified problem, the objective of which is to maximize the net profit to Sentinel Security. So I hear that word maximize, I think, hey, that's something that I want to hold on to. To Sentinel Security for supplying security service for T attendees. So T is the number of attendees. To the annual meeting in New York using the following decision variables. Okay, so it gives us that. X1 and X2. So let's just try to do this. So I wrote down everything I got from that. Sometimes you have to go through these things a couple times. And I want to think about my 3 things. I want to think about, maybe this we'll do it the first time in English. We want to, what can we decide? What are we trying to optimize? And what are our constraints? What are holding us back? What do we have to adhere to? What is contractual? What is limiting us? That's all goes in this third part. So what are we deciding? And let's just stay at English this first round through. What are we deciding at Informs? What do we decide? Our Sentinel Security, I think we work for. What do we decide? Just in English, what do we decide? Not in the math yet. What do we decide? What can we control?
The amount of guards we put on duty.
Okay, so we're trying to decide how many guards, right? Amount of guards to put on duty. That's correct. That's the thing we can control, right? Obviously, being a profit-motivated company, what are we trying to optimize? What are we trying to optimize? And when we say optimize, we think either maximize something or minimize something. What are we trying to optimize in this case? We're trying to optimize or make the highest what? Profit, okay? A lot of times it's going to be profit. So we want to max profit. Okay, what did I see in constraints there? What did I see in constraints there? So, what did I see? Well, okay. What did I see in constraints there? I know I have some constraints. What are some things that are contractual that I had to have? What was one of the things that was a constraint? Anything.
2 guards for every 1,000 people.
Okay, so we had 2, right? This was kind of a constraint. So in the evening, I need N guards, whatever that is, right? It could be 5, could be 10, but you know, they have something in the contract said I need N guards, you know? And you're right, during the day, we need 2 plus 1 for every 1,000 people. I think that was all that was in there, right? I think that was all that was in there. And there's probably other things that it would be part of that, but in this case, that's all we have, all right? So let's go from, and those 2 things need to be represented down here in the constraint area. So let's now make this a mathematical model. So our decision variables, it asks us to use the variables it tells us to use x1 and x2. Okay, it says x1 is the number of guards needed each day, of day guards, and it tells us x2 is the number of evening guards. We want to maximize profit, but we can't just say maximize profit. We have to represent profit in terms of the variables we've been given. And there was a sentence in there that told us what profit is. It says, net profit to the firm is attained by subtracting its payments to its guards plus the fixed expenses from the contract amount negotiated with and formed. So we got B dollars over Sentinel Security, we got B coming in, right? That's our fixed rate contract amount. We got B coming in. We have some fixed expenses, we have to subtract those out, right? We have to subtract out F. Those are fixed expenses. So maybe it's $10,000, we have $2,000 worth of fixed expenses. Minus, now we have our guard, our salary, right? Okay, so let's see, let's do day guards first. That's X1. So day guards are here for 3 days, from 8 a.m. to 6 p.m. That's 10 hours, right? So they're working 30 hours. Does that make sense? So 10 hours for 3 days. That's when the day guards are here. So it would be minus 30, and we pay them D dollars per hour. So minus 30D, they work 30 hours, we pay them D dollars an hour, times how many guards we have, right? So minus 30D X1. That makes sense? Our night guards, they're here for 4 nights, and they're working, looks like if these work 24 hours in a day, they work 14. 4 nights times 14, that's 56 hours in total. We pay them a lesser rate because less things going on in the evening apparently. So we pay them E, and we're not sure how many we're going to hire, so that's X2. So that is my objective function in terms of X1 and X2, right? Subject to, and now we need to represent this. The number of evening guards I hire has to be at least N. And it doesn't tell us what N is, but it has to be greater than or equal to N. That's a lower bound constraint. It has to be less than or greater than or equal to N. And then our day guards, we need 2. Okay, so that's X1 has to be greater than or equal to 2. And then we have to factor this in, okay? 1 for every 1,000 people. So if I have 1,000 people, how many guards do I need? At least 3, right? If I have 2,000 people, I need at least 4, right? So how are we doing that? We're taking the number of guards, right, and dividing it by 1,000, right? So So 1,000 divided by 1,000 is 1, 2 plus 1. So it would look like this. 2 plus T is the number of attendees. Okay, we don't know what that is. Divided by 1,000. If it's 4, hey, we're going to need 4,000 divided by 1,000 is 4. 2 plus 4 is 6. Okay, so we're representing that. A lot of times in these as well, I throw out my non-negativity constraint because I can't hire negative guards. And also in this case, what other constraint would I use? I can't hire negative guards. And what else can I not do when I hire like staffing? A lot of times this applies to staffing models, and this is kind of a staffing model. Yeah, it has to be in it. We can't hire 1.25 guards. Not the way we have it structured. We say we're either hiring you for 3 days or 4 nights, right? So we can't hire 1.16 guards, right? So we're going to say x1 and x2 are integers. And that's it, okay? That is the answer. I mean, that is, we've represented that situation mathematically as a mathematical model. Let's look at part B. It says, explain why this problem of maximizing net profit is equivalent to minimizing the variable cost of payments to its security guards. Anyone want to explain that for me? Why is this the same as minimizing the variable payments to its security guards? And it would give you the same answer. What's B and F? They're fixed. I mean, they're 8,000 or 6,000 or whatever they are. So we could do the same thing by saying, well, these don't matter. These are contracted. We could just minimize the variable expenses, right? Because the other stuff is locked in. It doesn't get affected by how many guards we hire. So if we solve this with this, it nets out to the same exact answer, trust me. So we're still optimizing our profit, but we're optimizing it by saying minimize the variable cost, right? The fixed cost we can't control, right? By hiring less guards or more guards. Informs expects 2,000 attendees. So what they're doing in part C is they're starting to fill in these things. Okay, they said they expect 2,000 attendees. So that's going to be T. If the contracted price from Informs is 10K, so this is 10K. It says, I think it says the fixed costs are 1K. Okay. And it's telling us Sentinels pays its guard $15 per hour during the day and $12 per hour in the evening. Develop a complete mathematical model at the Informs meeting. Okay, so now it's starting to go from a model shell to an actual model. So we're filling in the things we know now. All right, so D would be 15. So now this changes from 30D to 30 times 15 is 450, I believe, right? And E becomes 12. And 12 times 56 is, what is that? 672, thank you. Okay. And it tells us, this, if I wanted to, I could put this back as max. I don't know how it did in the book, but I could maximize. This is what, 10,000 minus 1,000. Change these to minus again. Okay. We have 2,000 attendees. So this becomes, well, plug that in. 2,000 divided by 1,000 is 2. 2 plus 2 is 4. I don't think it gave us n, did it? I think it gave us n yet, did it? Okay, so we got to leave that alone. So now we're developing. So what a model shell is for is, if you're doing a lot of these engagements, a lot of these things change. If you're doing one in New York City, the hourly rate's going to be higher than if you're doing one in Loretto, and the fixed cost is going to change, right? So a lot of times people develop model shells. And you think about it in Excel, it can be just a variable you plug in, like input these things here, and that's kind of what we're doing here.
Yeah, n equals 2.
Does it say it has to be? Okay. So then this would be 2. Thank you. Yeah, it says, I see in the first sentence, have at least 2 guards on duty each evening. So yeah, that n is equal to 2, thank you. Suppose attendance is expected to be 2,200. Now what would be the model? Okay, so if it was 2,200, well, that would be 2 plus 2,000, or 2,200 divided by 1,000. That gives me 2.2, which gives me greater than 4.2. And I think someone pointed out that the solution set said 4.4, which is wrong. It should be 4.2 here. But what, and that's fine to write it that way, but what is the first feasible answer for x1? It's not 4.2, it's what? It's not 4 either. What is the first feasible answer that it adheres to all of our constraints? 5, because it has to be greater than 4.2, and it has to be an integer, right? It's an and situation. All these constraints, and if you like logic, these are all and deals. This has to be true, and this has to be true, and this has to be true. So it has to adhere to all of those constraints. Okay? So that was probably, was that the most difficult one for most people? There's a lot going on there, right? There's a lot going on. Okay. What other one would you like to do?
Back to B.
Uh-huh.
I mean, I know if you're maximizing, you're subtracting, if you're minimizing, you're adding, but why? Like, why are you subtracting to maximize, and why are you adding to minimize?
Well, if you think about it, okay, we understand, we know that our profit is going to be, okay, let's look at this. It's 9,000, right? Because I know I'm getting 10,000 up front. It's a fixed contract. And I know my fixed expenses are 1,000. So I have $9,000 to work with, right? What's going to eat into that $9,000? There's only one thing eating into those 9,000. That's my profit right now, but I have to, unfortunately, do what?
Get guards.
Hire people, right? Okay. So if I can minimize hiring these people, right, this cost, it in essence maximize the end, right? So if I minimize my cost, okay, and in this case, when I say minimize cost, well, I'm saying cost, I want to keep it down. So these costs are adding up, right? Because we know in our minds that it's subtracting out for the net profit. So that's why these become positive, because we're trying to, minimize those expenses. Okay, trying to minimize those expenses. So if we said minimize the negative, what's going to say, hire 1 billion guards, right? Because the more guards you hire, the better you do. But that's not really true, right?
Yep.
So, okay. Good question. What other homework problems would you guys like to do? If you don't have any, I think I'm going to do 7. On page 41. Okay, so 7 says, and what I'm trying to show you here is that, there's not just one way to look at a situation. Okay, there's, if we were investing money in a portfolio, one person might say, hey, I want to maximize my expected growth, right? So I'm going to invest real aggressively in all kinds of aggressive stocks and penny stocks. And that's their model, right? They're maximizing potential growth. And someone else might invest in a portfolio and they say, I want to minimize my risk. So they invest in, money markets and annuities and maybe bonds, something like that. But there's still, still a portfolio optimization model. This is not as good of an example, but it's an example of that. So let's look at number 7. It says, sometimes different managers or executives approach the same data with different objectives. Circuit Guys, which I guess is calling out to Circuit City, which is no longer a business, is a retail computer store that displays the latest computers from Compaq, no longer in business, and IBM in business, but I think they sold out all their retail machines. machines to Lenovo. The store averages a profit of $200 on every compact system sold at $300 on every IBM system sold. For each compact system displayed, the estimated probability that circuit guys will sell the system on a particular day is 2%. Each IBM system displayed has an estimated probability of 1% of sale on that day. Okay, so this one's not asking for the complete model, it's just, we're just focusing on the objective function, if you will. It says one manager at Circuit Guys suggests that since this is a new store, it should maximize the total number of units on display. Write the expression that models this objective. So let's go up here. Let's see if we have any wiper fluid. And the first thing we need to do is to define our variables. And you know, for defining variables, use whatever makes sense to you. Okay, if it's the x1, x2 makes sense to you, use x1 and x2. If a, b makes sense to you, that's fine. Or, you know, I think I'm going to use C and I, okay, because that makes sense to me. Compact and IBM. So my decision variables are C is number of compacts, and I is number of IBMs. And I think to display. Okay. So the first manager says, and this is kind of an odd way of looking at something, but he wants to maximize the number of units on display. Pretty simple. C represents the number of compacts on display. I represents the number of IBMs on display. Maximize C plus I. That's it. Okay. Now in reality, you know, if this is all the model was, we'd display an infinite amount of compacts, an infinite amount of IBMs, because that maximizes them. But in reality, what does a retail store have limiting them so they can't display an infinite amount of goods? One thing for sure is what? Space, right? They only have so much shelf space, right? Maybe 20 square feet, whatever it is. Okay, that's one of the constraints that we don't have here, but it's reality. B says, another manager feels that the way to impress corporate headquarters is to show a large number of sales, units sold, it's talking here, okay? Write the expression that models this objective. Well, it's telling us, and this is kind of a crazy way to look at things, and it doesn't work this way in real life, but it says certain guys will sell the system on for each compact system displayed. The estimated probability that certain guys will sell a system on a particular day is 2%. I'm just going to write that up here. And for every IBM, 1%. So basically what it's saying is, if I display 100 compacts and 100 IBMs, and it's, I know this isn't reality, I would sell 2 compacts and 1 IBM, right? So it's saying somehow, in some bizarro world, that the number of units I display directly relates to how many I sell. So that would be 0.0, I would want to maximize 0.02C plus 0.01I. Now my brother manages the Lowe's in State College, and he does say that if he takes, like, for example, air conditioners, doesn't change the price on them, but they move them to, like, you know, you ever see those like little stacks they have at the front of the store? It'll like triple sales, just because they, you know, people see it and they think, oh, this is special, and they don't change the price at all. So there's things like that going on. Part C says, still another manager maintains that the bottom line is what is important. He feels that in the long run, maximizing expected profit for the shareholders want. Write the expression that models this objective. It says we make $200 on every compact, so let's put $200 here, sold, and we make $300 for every IBM. So let's see. C says maximize 0.02C. That's how many we sell, and then we make $200 plus 0.01I, and we make $300. So anytime we have constants that we can multiply out, we should. So this was 0.02 times 200 is 4, I believe, and 300 times 0.01 is 3. And we get maximize 4C plus 3I. Now in the real example, like you said, there's going to be shelf space limitations. A lot of times organizations have contracts that say you have to display at least this many of our product, right? They even have contracts where they have to display it, like the end caps, you know, in the grocery store, you know, when you walk around, that's like real prime real estate. At eye level, they have, you know, all kinds of constraints like that. So this is kind of a non-realistic example, but what it's trying to show you is that, you know, the objective function just doesn't have to be one way of looking at a situation or issue. Okay. Other questions you guys might have? How'd the homework go in general? All right, I guess? Had to consult with solutions maybe a little? It is to go from a word problem like these cases to the model. It does take some time, you know, it does take. But I promise you, as we do these, and we'll do more of them this week, you know, you'll just start, as you read a sentence, you'll start saying, oh, that's a constraint, or that's the thing I'm trying to optimize, or that's the thing I can decide. It'll just kind of come out at you, right? I know it will. It happens. Okay. Other questions? This is your time to ask questions on the first week. If not, we'll move on to the new material. Okay. Let me get that set up then.